Okay, one more thing here to wrap up our limits intro 2.2 and 2.3. Let me go to my lecture. Here's where we left off. These infinite limits, kind of keep in mind, if you're trying to figure out if the answer, once you know there's a vertical asymptote, if you're trying to figure out, is it headed toward positive infinity or negative infinity? There's really no way around it. We got to use a table. Okay, for each case. The two-sided, got to use two tables and make sure they go in the same location. All right. The last topic for our intro is the squeeze theorem, our first theorem of the course, first of several. The squeeze theorem is obviously a theorem about limits, and it's kind of cool. And we'll see where the name comes from. I mentioned squeezing in the last video. I think that was no connection with that last example, like the vertical. Anyway, all right. So this squeeze theorem, I'll just go ahead and read it. If we've got three functions, f of x, g of x, and h of x. If f of x is always less than or equal to g of x, which is always less than or equal to h of x, and the limit as x approaches a, the limit of f of x as x approaches a, is equal to the limit of h of x as x approaches a, and we're going to say both those are equal to L, then what could we say about the limit of g of x as x approaches a? So imagine, right, f, g, and h. F is always smaller than g, which is always smaller than h. We know that f and h, as they approach a, they're coming to the same point at L. So the idea is g gets squeezed in between them. What would have to be the limit for g of x as x approaches a? We were in a class, I would say, okay, take 10 seconds to think about it, and then maybe somebody could guess what it would equal. I'll just tell you. It's equal to dun, 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 L. Why would that be? If the bottom function is headed toward L and the top function, the bottom function is headed toward L and the top function is headed toward L, then if something was in between them, well, it's getting squeezed between them, it's going to have to go to L as well. So hopefully this picture makes it a little bit more clear. Here's f, always the bottom function. H is always above the other two. Notice they can equal each other, though. That's allowed. So at this one moment, all three are equal. And we see that g, if it really is caught between the other two, it has nowhere to go. It gets squeezed between f and h, and it has to pass through that same value at L as well. So the limit for g of x as x approaches a is also L, along with the others. Okay, kind of interesting, like the drawing. How's this going to be useful? We've got one example at the bottom there, the limit as x approaches 0 for x squared cosine 1 over x. So I'm going to hop over to my paper here on the side. The limit as x approaches 0, x squared cosine 1 over x. How are we going to take advantage of the squeeze theorem? Okay, so the squeeze theorem, it has these three functions, right? F, g, and h. Right here, this is going to be our g of x. We don't know what f of x is yet, or h of x is yet. But if we're trying to take the limit, it must be the g of x that we're looking at. How are we going to create the f, and the h. How are we going to figure out what those are? Here's what we're going to do. We're going to start with something we can all agree with, and then we're going to build from there, and we're going to see the f less than or equal to this g less than or equal to the h. Check it out. This has a cosine involved. Let me just take that portion, and I know it's not the whole thing. We're going to get there. Turns out cosine, and this is the cosine of 1 over x, but really this would be true of the cosine of anything. The cosine is always stuck between two values. This would be better if we were in a class. I'd say, hey, what y values is cosine always caught between, that it can never go less than this number and never go bigger than this number? And usually people have the answer to that, or a few people in the class, that cosine is always between -1 and 1, the y values. Right? We happen to have the cosine of 1 over x. That's not important. We know the cosine of anything is always somewhere between -1 and +1, and it can equal those. Right? So we're gonna just start with this true statement. We all agree with this. Okay. From here, we can build our g of x in the middle. Multiply all 3 by x squared, and we'll have it. So I want to multiply the middle by x squared to create my g of x. But if I do that, I have to do it to the outsides as well. -x squared here, +x squared here. So I've got my g of x, and now I can see -x squared is what I can use for f of x, and +x squared is what I can use for h of x. Now, oftentimes students, this problem, it takes a little bit more creative thought, right? It's not just like, hey, follow this procedure and your number is a little different, right? It takes a little bit more thinking and planning, right? How did we know to begin there? It was just a true statement. You can always begin with a true statement and then build off of that. How did I know to just take the cosine? Well, because that's the true statement related with cosine. It didn't have the x squared, so then I needed to include it by multiplying each piece by x squared. And now, if this is true, this has to follow. And when that kind of clicks, you're like, okay, it's one thing to kind of, yeah, that's true, and this follows, sure. It's another thing to do these problems on your own. And that's just deeper level thinking and problem solving. And, that's just kind of a normal thing to develop, a normal thing that we'll do at this level of math and beyond. Okay. So if you're satisfied with that, we've got f, g, and h. We're going to look at the limits for the f and for the h. And those two together are going to tell us our answer for the g. So we're taking the limit as x approaches 0. So let's apply that to this bottom function, -x squared. Well, it turns out I can easily plug that in. There's no holes or jumps, right? That's equal to 0. Let's do something similar for the h. The limit as the limit as x approaches 0 for x squared. Well, here I can just plug in as well. There's nothing unusual. I can plug in, get an answer. That is also 0. And here's where it all comes together. We got the same result for the limit of f and for the limit of h. They came out to the same thing. Well, if f is always less than g and that's always less than h, yet at this one point they're coming together at 0, then what must be the limit for what we're really investigating this whole time, the limit as x approaches 0 for x squared cosine 1 over x? Well, I don't need to plug in. In fact, I can't because I'd be dividing by 0. It's kind of, maybe I should have mentioned at the beginning, we can't just plug in. But we know because these are both going to 0 and because of the relationship between them, that this must be going to 0 as well. Let's take a look at, guess what, the graph, and we'll see it like, okay, yeah, I see that squeeze theorem. These both go to 0. This one's getting squeezed in the middle. It has to be going to 0 as well. It's pretty cool when you see it graphically. Y equals, here's the function that we care about. Excuse me. X squared cosine 1 over x. And kind of if you zoom in, kind of you zoom out, it's kind of funky, right? You wouldn't expect that. And then it's almost like there's like teeth or something, you know, right there. And it's kind of wiggling, you know, back and forth. And at 0 itself, oh, well, it intercepts the x-axis so many times. It's trying to highlight all the x-intercepts. Okay, well, it's undefined at 0. We can tell that. So what if we graph negative x squared? Ooh, take a look. Negative x squared is always below, but there's a couple of moments where it's actually equal, and 0 is one of them. Like all those kind of, all these spots. Ooh, that's really interesting. And how about positive x squared? Oh, wow. Okay, so we've always got the black, then the purple, then the red on top, and they all come together at 0. So the limit for the F, the black, is coming in at 0. The limit on both sides for the red coming into 0. The purple is definitely squeezed in between them, right? And it's kind of like bouncing back and forth. So it's getting squeezed in. And even though there's a hole at 0, that limit we can tell because of the squeeze theorem would be equal to 0 as well. All right, really, really cool, really fun. That is it for 2.2 and 2.3.